So when we started this series titled as Artificial Intelligence, we already mentioned that what is going to be the agenda of this particular course. So it is about the study of intelligent agents and study of intelligent systems, and how these intelligent systems and intelligent agents actually work. That was the basic bottom line behind this course. And now with this platform, just try to think that how a particular artificial intelligence agent is going to prove a theorem, how it is going to look into a statement which is comprising of some facts and then say, okay, this is fine or this is not fine, this statement is right or this statement is wrong, or even this particular theorem is this particular theorem can be proved and this particular theorem cannot be proved. So for that we need to use some kinds of techniques, and our today's lecture is about one of such techniques, which is named as resolution. Now let us first of all understand what is resolution, and then we will go to the components of resolution, and then we will look definitely a few of examples, because resolution in the study of these agents is actually a very important topic. So resolution, when we talk about it, is kind of a logical method that is used to validate the statements by showing that assuming the negation leads to a contradiction. So basically this is refutation, this is proof by refutation, we can say. Essentially the technique of resolution assists the truth of the claim by presuming that it is false and then proving that this assumption is impossible. So kind of a proof by contradiction, as we say. This resolution is actually a rule in first order logic. And what is this first order logic? That we have seen in our previous lecture. So first order rule in first order logic that allows us to derive new conclusions from previously established data, and with the help of this concept of proof by contradiction or proof by refutation, if assuming something is incorrect results in a contradiction, then the assumption must be true. So this is the kind of, we can say, mechanism, that kind of know how, that how are we going to pursue the resolution in case of these AI agents. Moving forward, your resolution is actually we can say it is a widely employed approach in logic based problem solving and automated reasoning, because it produces systematic, thorough and efficient proofs of logical statements. Now when we say resolution and look into the usages of resolution, it is commonly used in various fields of artificial intelligence, like automated, it could be automated reasoning, and some theorem proving or something of that sort. Now what are the key reasons behind choosing this resolution technique for all this theorem proving and automated reasoning? So this resolution prove the statements logically. It uses the contradiction to assess if a statement is true or false. So that is the first kind of, we can say, reason, or that is the first idea, that why we are using this resolution. Another one is automate logical reasoning. Basically resolution with its own kind of implementation allows the computers to automatically draw conclusion from whatever facts have been kind of provided. It also solves the problem in AI and logic programming. It is mostly used in Prolog and other AI applications for rule based reasoning. Also it ensures consistency in knowledge based system, because basically it assists in detecting the inconsistencies and maintaining the valid information. Also it verifies softwares and systems both. It ensures that the software, security protocol and hardwares are working properly. So, we have kind of reasons behind choosing this resolution for our work or in any kind of field of artificial intelligence. So, these are it proves these statements logically, it automates the logical reasoning, it solves the problem in AI and logic domain. Also, it ensures the consistency in knowledge based systems, and it also verifies softwares and systems. Now, before going into how are we going to perform or how to implement resolution, we need to understand that what are key components of resolution. So, the first key component of resolution is a clause. So, clause is basically a disjunction of, I can say, literals that serves as a fundamental units in this resolution based proofs. So, what are the examples of these clauses? So, we have Px negation Qx. These kinds of expressions consist of two literals which can be linked by either or or we can say and. Or for example, we have negation of A, B, C. If we say negation of A, B, C, this expression includes three literals, meaning at least one of them must be true, because here we are talking about this resolution based proof. So, these kinds of examples will lead us to understand that how these literals can be connected, or what actually a literal is, and a clause is actually we can say is disjunction of a literal that it serves as a fundamental unit in these resolution based proofs. Now, let us consider a statement which says for every x there exists some y such that x loves y. Now, what do we need to do? We need to consider this statement, and then in the next step we need to convert this statement into an FOL format, first order logic format, and also the propositional logic, but propositional logic or first order logic is the extension of propositional logic, as we have already kind of understood this fact. So, in order to translate this statement which is for every x there exists some y such that x loves y, we need to have an kind of FOL representation, and the statement itself says for every x. So, when we are looking into for every x, that means the quantifier which we are going to use with variable x is going to be for all, and there exists some y. So, definitely the quantifier which is to be used with y is going to be there exist and such that x loves y. So, we will simply use the predicate loves x comma y, which means that x loves y. So, for all x there exists y loves x y is going to be the complete and the correct translation of that particular statement into the first order logic. Now, here at later stages, what do we need to do? We need to remove this existential quantifier and the corresponding variables also. So, that means here I am talking about y. So, in order to remove y, we introduce a column function which is f x, resulting in x loves x comma f of x. So, in place of y, we have written f of x, where f of x represents a specific person that x loves, making the statement fully quantifier free. Now, why do we need to make these statements quantifier free? Because before resolving the clauses, or before what we can say, before applying the resolution on the first order logic statements, we need to convert them into the clausal normal form, and in clausal normal form we cannot we will not be entertaining any quantifier which is either your for all or your there exists. So, those quantifiers will have to be removed in one way or the another, and scolumization or use of scolum functions is actually one of that kind of technique that we will see when we will look into the conversion of FOL into CNF. That time we will look into it into details. Now, the first key component in resolution was a clause. Moving on to the next key component, we have literals. Literals is either the atomic preposition which we can say fact or its negation. So, literals are building blocks of the clauses, and the examples of literals could be anything, like for example, P of x is a positive literal, that either it is going to be true or false, and negation of Q of y is a negative literal which is negation of a fact. So, these are these we can call P of x as a positive literal, and negation of Q of y is the negative literal. So, basically atomic preposition or facts, or it could be the negation of any atomic preposition or negation of any fact. Then what do we need to do in resolution is unification also. So, the task of unification is, we can say, it is the operation of two logical expressions by determining the correct substitutions for the variables to make both expressions equal. So, now we have two expressions and we want to equalize these two expressions. So, for making these expressions equal, we need to do some substitutions, and this is what the unification is. So, let us understand the unification with the help of an example. So, let us say we have two predicates. So, predicate 1 is loves x comma Mary, and the second predicate is loves John comma y. Now, if we want to unify these two predicates, we have to find the substitutes for x and y such that these two predicates will become identical, and if we substitute x is equals to John and y is equals to Mary, it gives us loves John comma Mary, which is a correct preposition without any kind of, we can say, variable, and we have used the process of unification in which substitutions of variables is being done in order to make the two predicates kind of identical. So, after the unification we can say both predicates are same, because x has been kind of substitute with John and y has been substituted with Mary. So, both the predicates loves x comma Mary will become loves John comma Mary, and loves John comma y will also becomes loves John comma Mary. So, now these two predicates are identical. So, this is what substitution is. This is what unification is. Now, next moving on to substitution. Substitution is actually the replacement of variables by definite values or words in a logical formulation for some kind of scientific expressions. It is used in unification, it is used in resolution and the inference rules to make logical assertions more specific. Now, let us consider the example of your substitution. So, we have a predicate with a function which says teaches, and the first argument is professor, comma, and the second argument is subject. Now, we need to substitute professor, we need to substitute Dr. Smith in place of professor, and we need to substitute mathematics in place of subject. It yields the result in teaches Dr. Smith comma mathematics. So, which indicates that Dr. Smith teaches mathematics. So, this is actually kind of substitution in which we are replacing variables by definite values, and the previous one was unification in which we actually want to make the two predicates identical. So, the agenda of unification and substitution is entirely different. Here two predicates are to be made equal, while in substitution you are just you can say replacing some variables with the definite values, or we can say kind of constants. So, this is what substitution is. Now, another step which we need to explore in our upcoming slides is about escolumization, which I just spoke about. It is actually the process of removing existential quantifiers by introducing some escolum functions or escolum constant. So, that is the process of escolumization, and that we will definitely look into that how this escolumization is done with the help of examples when we convert our FOL into CNF. Now, what do we need to do? So, the idea with which we started this topic was we need to perform resolution, or we need to implement resolution in order to make an AI agent smarter. So, the resolution process that actually involves systematically modifying logical statements and then utilizing the unification, substitution and other resolution principles to either derive a contradiction or establish the desired outcome. So, this is what your resolution should do in a way. Now, what are the key steps of performing this resolution in the first order logic? So, there are kind of some definite steps which are involved in first order logic resolution. Now, what are those steps? We will look into, and then one by one we will explore that those steps and do resolutions with the help of examples. So, the first step says we need to convert statements to first order logic and express the given information using the FOL notation. So, for example, I have given one statement that John loves Mary. So, a corresponding first order logic statement has to be written and the given information has to be expressed using this first order logic notation, in which we can say loves could be a predicate with two arguments, John and Mary. So, something of this sort. We have plain statement, English like statements, and we need to convert them into first order logic notations, FOL notations. Now, after conversion of FOL, after conversion of simple statements into FOL notations, these are needed to be converted into CNF, which is clausal normal form, and in conversion of CNF, some steps are to be done, which is implications are removed, negations are moved inward, then variables are standardized, escolumization is to be applied, and then finally some distribution is to be done, and your FOL sentence or your FOL notation corresponding to a sentence has to be converted into the conjunctive normal form, or clausal normal form, we can say. Then the next step is whatever assertion we need to verify, we need to negate that assertion, because we are going with the proof by contradiction. So, assume that the negation of the goal is true and include that in the list of clauses. That is the next step. Then we need to apply unification, which is finding of relevant variable substitutions to make literals or to make predicates look like identical. And then we need to use the resolution rule also, that is we will identify complementing literals and resolve them to create new clauses. Now, what is a complementing literal? So, let us say for example, we have one literal which says teaches Dr. Smith comma mathematics, and the complementing literal is negation of teaches Dr. Smith comma mathematics. So, these kind of complementary literals we need to look for, we will cancel them out and or we can say we resolve them, and then we will create new clauses, and this step will be repeated until a contradiction or a proof is found. So, that means this resolution will be continued until an empty clause is derived, which is definitely a contradiction or the goal statement is proven. So, both can be the ideas, but as far as our scope is concerned, we are more into exploration of this proof by contradiction. Now, here among all these steps we have looked into the unification, then negation of assertions to be verified is not at all a complicated thing, and in the previous lectures we have also seen conversion of a statement to first order logic. What is remaining here is, which we have not seen till now, is conversion of FOL sentence into clausal normal form or conversion of FOL into CNF. Now, this is the step, or this is one of the key things in the resolution which we still need to explore, which we still need to understand. Fine. But before going into the nitty-gritties of conversion of F-fold into clausal normal form, first of all let us understand that what actually this clausal normal form is. So, clausal normal form is actually you can say it is a sub-language of first order logic. Clause, as I have already told you, is an expression of the form L1 then L2 till Lm, where Li is a literal. So, basically clause is a disjunction of literals. Empty clause will have no literals, no modals, nothing, and clauses are denoted by uppercase letters with some kind of with some script, which is kind of we can say subscript. Now, there are some satisfiability preserving transformation from first order logic to CNF, and that is what we need to do. This basically says that if a set of first order formula are satisfiable, then their CNF is also the satisfiable. Conversely, if the CNF of a set of formula is unsatisfiable, then we can also say the formula are unsatisfiable. This is then useful for showing the logical consequences, and this also established the fact that CNF is easier to work with and is the form used by resolution inference rules. So, CNF basically clausal normal form, where each clause which is a disjunction of literals and each clause is connected with the logical connective end, we can say. Now, let us try by a very simple example that how are we going to do this proof by contradiction. Here we will take some given axioms which are already kind of in the notation of formulas. We will we will convert them into CNF, negate the goal which is to be proved or negate the statement which is to be proved, and then resolve the things. So, first very simple example of refutation or proof by contradiction, or we can say simply the resolution method which is using the technique of refutation. Now, let us say we take an example and we have been given some axioms. These there are axioms which says P implies Q, Q implies R and negation of R. These are the three axioms which are already given to us, and what do we need to prove, or what is the goal? The goal is negation of P. Now, what are we going to do? In the next step, we will convert all the three axioms into clausal normal form. Now, clausal normal form says every kind of we can say statement has to be in the form of the disjunction of clauses, or we can say conjunction of clauses, and clauses are in the form of disjunction of literals. So, in order to convert P implies Q into CNF, we have an equivalence rules which says negation of P or Q, that is sufficient here. Then Q implies R is going to say negation of Q or R, and now the clauses will be, the earlier clause was P implies Q, Q implies R and negation of R. Now, we have with the help of equivalence rules converted P implies Q and Q implies R, because this implication is not allowed in clausal normal form. We need to remove this implication or by implication, and because of that now the clauses which we are having is negation of P or Q, then negation of Q or R, and then there is negation of R. And apart from these three clauses, we have a goal also which is negation of P. Now, in the next step, what do we need to do? We need to add the negation of goal in the clauses. So, in order to prove negation of P, which is our goal, we are assuming P. So, P is something which we have assumed, and we will add this into the clauses and then resolve those clauses. Now, we take the first among the available clauses, we have negation of P or Q, negation of Q or R, we have negation of OR, and apart from that we have P also. So, now we are going to do some resolution steps. So, the first resolution step says you need to resolve 1 and P, which says negation of P or Q and P. So, P and negation of P, we can say in a way they cancelled out, and what we are left with is only Q. At the second step, we will be resolving Q and the second clause, which was negation of Q and R. So, negation of Q or R, sorry. So, negation of Q or R is resolved with Q. So, again negation of Q and Q will be cancelled out, we will be left with R only, and finally in the list of clauses we have R and negation of R. So, R and negation of R when resolved together, they result in an empty clause, and empty clause is considered as a contradiction. So, finally, we have obtained an empty clause which is a contradiction, and on obtaining of contradiction we say that whatever we have assumed was false. So, we have assumed P. So, if P is false, then negation of P is definitely true, and this is what your proof by contradiction, which is more specifically known as refutation, is. So, here in this example we have just taken a very small example in which there are only 3 statements, only 3 clauses were there with a very small goal, and all those we have not given the statements related first order logic representation was also available. In the upcoming examples, we will be taking statements, convert them into FOL, and then perform the whole resolution thing onto it. So, that is all from my side for this particular lecture. Here is a list of references which is being used for the preparation. I hope you have enjoyed this one. More is to be covered in resolution in the upcoming lecture. I will see you in the next one. Till then, take care. Goodbye.